How Python manages memory. Python's memory management is one of its most powerful features, and it works quietly behind the scenes to make your life easier. When you write Python code, you don't have to worry about where memory comes from or where it should be released. This is very different from languages like C or C++, where developers must manually allocate memory and free it themselves. In Python, all of this is handled automatically, allowing you to focus on writing clean and reliable code instead of managing memory. Python's memory architecture is built in clear layers that work together seamlessly. At the lowest level, Python requests raw memory from the operating system. On top of that, the Python Memory Manager organizes this memory into pools that Python can efficiently control. Different object types are then handled by object-specific allocators, which know the best way to store things like integers, strings, or lists. Finally, reference counting and garbage collection work together to track objects and clean them up when they are no longer needed. Let's do some coding examples here. Every Python object has a size in memory. An integer has its size, can be 28 bytes. A string gonna have size, 46 bytes. List gonna have size, 104 bytes. And even empty objects consume memory. Let's see the result. Here we go. Why does an integer take 28 bytes? Because Python stores more than just the value. An integer takes 28 bytes in Python because Python stores much more than just the numeric value itself. Along with the value, Python keeps type information so it knows the object is an integer, a reference count to track how many variables are using it, and extra metadata needed for memory management. Python does this to make integers safe, flexible, and efficient to use across the language. By storing this extra information, Python can handle automatic memory management, support dynamic typing, and avoid many low-level errors that occur in languages where only the raw value is stored. Memory allocation is the process by which Python reserves space in memory when your program needs it. Whenever your code creates data, Python automatically finds free memory, uses it, and keeps track of it while the program is running. You don't have to ask for memory or release it yourself. Python manages this for you, making sure memory is available when needed and reused or freed when it's no longer required. Let's do some coding. This example shows how memory allocation works in real Python code. When the function runs, Python allocates memory to create a large list and stores it in memory. As long as the list is referenced, the memory stays allocated. Even after the function finishes, the memory is not freed immediately because the returned value is still referenced by result variable. Only when that reference is deleted does Python know the object is no longer needed, and the memory can then be deallocated automatically. Python uses a private heap to store all data and objects, but you never access it directly. Python manages it for you. To optimize memory, Python caches small objects like integers from -5 to 256, single character strings, and empty immutable containers. For example, small integers and short strings often share the same memory, while larger numbers or longer strings usually do not. You can also force Python to share memory for longer strings using string interning, which helps reduce memory usage and improve performance. First, we create two small integers with the value 256. Python doesn't create two separate values here. Instead, it reuses the same one in memory, so both variables point to the same place. That's why the comparison returns true. Next, we try the same thing with larger numbers. This time, Python creates two separate values in memory, so they don't share the same space. Now, let's look at strings. Short strings like hello are often stored only once, so both variables share the same memory. But longer strings may not be shared automatically, even if they look identical. Finally, we force Python to share memory using string interning. By interning the string, Python stores it once and reuses it everywhere, which helps reduce memory usage. This is Python memory optimization working quietly in the background. What happens to a Python object from the moment it's created until it disappears? Every object has a simple life cycle. It is created, then used while the program needs it, and finally destroyed when it's no longer needed. Python handles all of this automatically in the background. Let's have a look at the life cycle of a Python object from start to finish. First, the object is created. Python allocates memory and the object becomes available to use. Next, the object is used. You can create more references to it and it stays alive as long as at least one reference exists. Finally, when all references are gone, the object is destroyed and Python frees the memory automatically. Now let's have a look at a real-world example managing database connections. So here we have a class that represents a database connection. When we create an object from it, the connection opens automatically. The cool part is what happens next. We use the connection while our function runs, and then without doing anything extra, it closes automatically when the object is destroyed. This way, all the resources are cleaned up for us, and we don't have to worry about memory or leaving connections open. It's a simple but powerful example of how Python handles the object lifecycle. Now, let's dive into Python's memory management system. I'm talking about the second layer. Remember, we had the OS layer and then Python memory manager layer. Specifically, we are talking about the PyMalloc allocator, Python's secret weapon for handling small objects efficiently. So what does PyMalloc do? It uses a hierarchical structure made up of 3 levels: blocks, pools, and arenas. This system is designed to handle objects that are typically 512 bytes or smaller, and it does 2 critical things. It minimizes how often Python has to ask the operating system for memory, the first layer, and it reduces memory fragmentation. Let's break down each level of this hierarchy. First, blocks. Blocks are the smallest unit in the system. Think of a block as a fixed size chunk of memory that holds a single Python object. The size of each block depends on what we call a size class. So you might have 8-byte blocks, 16-byte blocks, and so on. Next up, pools. A pool is a 4 kilobyte page of memory that Python gets from the operating system. Each pool contains multiple blocks, but here is the key. All the blocks in a single pool are the same size. Python maintains a linked list of pools for each size class. Why does this matter? Because when an object is deallocated, when Python no longer needs it, that memory can be instantly reused by another object of the same size. This design is brilliant for preventing fragmentation. Finally, arenas. Arenas are the big containers at the top of the hierarchy. On 64-bit systems, an arena is a massive 265 kilobyte chunk of memory that Python requests from the operating system. Each arena is divided into 64 pools. Now, here is something important. Python only returns an arena to the operating system when every single of its 64 pools is completely empty. In long-running processes, this is actually pretty rare. So why does Python use this complex system? Three main reasons are efficiency. By reusing memory internally, Python avoids the constant overhead of asking the operating system for memory every time you create a small, short-lived object. Fragmentation reduction. Grouping blocks of the same size into pools essentially eliminates internal fragmentation within those pools. And performance. Keeping related objects close together in memory within the same arena improves CPU cache performance, making your code run faster. Let's look at this code that tracks memory usage in real time. We have a memory tracker class with an empty list to store objects. The createObjects method runs a loop that creates list objects. Each list has 100 elements where the number I is repeated 100 times. Every 1000 objects, we calculate total memory by using sysgetSizeOf on each object and summing them up. Then we print how many objects we have created and the total bytes consumed. At the bottom, we create 5,000 objects and watch the memory grow. Let's see that. Whoa, look at that. So, what's the purpose of this? This makes invisible memory usage visible. It shows us that every object has a real memory cost and that cost adds up fast. In real applications, if we are not careful about creating and holding onto objects, we can quickly consume gigabytes of RAM. This is also a practical debugging tool. If our program is eating memory, we can use similar code to track down exactly where it's going. This demonstrates that memory management has real, measurable impact on our code. I hope this video was useful for you. You can like and subscribe. And thanks for watching.